Now that you've studied the diprotic titration and you solved the problems on diprotic acid or base titration, switching to triprotics is pretty much the same as the diprotics with one extra jump. Okay? So whenever we take a triprotic acid like H3A, when we're titrating it with a titrant OH minus, then we have three possible reactions. The first is the H3A reacting with OH minus. Of course, you guys can continue it to becomes H2A minus plus water. Clearly, this is the base, that's the acid deprotonation. And you have a K reaction, which is the Ka1 divided by Kw. You can continue, and that reaction is pretty much, if you will, this represented by this titration curve on this part, where we have it as if it's a mono acid titration. So here we would start off with H3A, and at the first equivalence, we would produce H2A. All of the H3A would be converted. And then after this, that's the difference, is that I still have H2A minus, which can react further with OH minus. And when it reacts further with OH minus, now I add the second curve, okay, and with the second curve, the H2A gets converted to HA2 minus. Up until here, it looks like a normal diacid, and we have a third jump where the HA2 minus becomes A3 minus. So we have three equivalence points, we have three jumps in the pHs, and if you want inflection points, we would have to add the pKa, because at pKa1, which is the half equivalence one, at pKa2, the second half equivalence, and at pKa3, we would get the third half equivalence. Now, that's it. That's the titration curve. Now, one thing I do want to point out that that's what we have in theory. Now, of course, remember that each jump here in pH, or each, grade change in pH, depends on the Ka value. And if the Ka value becomes very small, for example, the Ka3 at this area, the Ka3 is something like 10 to the minus 12, and that's very small. So this jump here will actually not appear as a jump at all. And that was a theoretical curve. This is what the real curve actually looks like for particularly H3PO4. So if I look at H3PO4 and I'm looking at its titration curve, that's what it looks like. There you go, that's it. If you look at it, it looks to me as if there's only two jumps in the pH. And so if I was just given this titration curve with this look, I really would have thought it would have been a diprotic acid and not a triprotic one, because here we go, in this area, or here, this is the same curve. In this area, this doesn't look much like, an equivalence point at all, or a change in pH of a jump type. Okay, but it is. Okay. Now, that's just the way it is with many of the triprotics, again, where the Ka3 is fairly low. Okay, so here we have, yes, my third equivalence point, and where I have produced the PO4 3 minus right at the end, and left, okay, at the third equivalence. Okay. So of course you should be able to get the pH at every single value in this curve. Now, I'm not going to go through these pHs. You could go ahead. First of all, you have H3PO4. That's just a weak acid, and depending on the Ka value, you choose the equation which is best suited to solve for that. And from now, I'm going to tell you the Ka is quite high for H3PO4, so it's very likely that you're going to need a quadratic equation to solve for the pH of this type of an acid. Of course, at the first equivalence point, we have H3PO4 will be H equal to the H2PO4 minus, and then as we add more base, the H2PO4 will be converted to more H2PO4 minus up until all of my H3PO4 original moles becomes H2PO4 minus at the first equivalence. And then I start my second titration curve, if you will, where the H2PO4 minus is reacting with more OH to produce all the way to HPO4 2 minus. And at half equivalence, yes, these two species right there, H2A and HA2 minus, are equal to each other. Of course, this is an easy, at the first equivalence, this is an easy pH to calculate, which is, since H2PO4 minus is an ampholyte, the pH is going to be pKa1 plus pKa2, which it houses both, okay, divided by 2. Now here at the second equivalence, the pH here is going to be equal to pKa2 plus pKa3 divided by 2. So watch out for the pKa values. They, it's a little bit, just a tad bit harder than diprotics because you have to think about which pKa values to use. And of course, at each of the half equivalents, at this first half equivalence, I have pKa1, second half equivalence pKa2, third half equivalence, I just have the pH will be equal to pKa3. And my final third equivalence, I only have PO4 3 minus, and depending on the concentration of PO4 3 minus, if it's greater than 100 Kb3, then I will choose the proper equation for that base, okay? Again, most likely that will also be a quadratic equation. Okay. And now, of course, at first equivalence, if that's the volume at first equivalence, the volume at second equivalence will be 2V at equivalence, first equivalence, and the volume at third equivalence will be 3 times the volume at the third equivalence. And this is now the real point we want to get into, and that is looking at the predominant species at different pH curves. And this is actually just representation. So here we have our graph again of this triprotic. Again, it looks like a die, but don't worry about it. There is a little bit of a hump up here. See, if this was straight down, then it's a die, but there's a little bit of a hump, and therefore we say it's a triacid. Okay, so now we're going to convert this into species present at different pH. So let's look at this initially. Initially, I only have H3PO4. So my species is mainly H3PO4. And of course, when I put H3PO4 in water, automatically, guys, remember that question number 21, even H3PO4, we do get all the species being present, since H3PO4 in water will give you eventually, we can calculate the concentration of the rest of the species presence. So there's no such thing as 100% H3PO4 in solution, because that H3PO4 does dissociate, and its Ka value is quite high. It's a pKa of 2.1. So you do get some of the other species in reasonable amounts, or in some amounts, okay? It's still a weak acid though. Now, so we start off with H3PO4, and then that H3PO4, as we add base, pH increases, it starts to decrease in solution, and the H2PO4 in red starts to become greater, okay? Up until all the H3PO4, or most of it, becomes 0. Of course, we get some back reaction with some of it. all of it gets converted to H2PO4 at the first equivalence, okay? Yeah. At this, and so here, the conjunction between these two lines is the pKa, or the pH at the pKa1, where I have equal amounts of H2PO4 as I have of H3PO4 as I have H2PO4. That's the pKa, so I can go back and get the pH at pKa1. Okay, so this is the equivalence point where I have no more H2PO4, all of it becomes H2PO4. Now my H2PO4, also in red, starts to decrease as my HPO4 in green increases. At some point they become equal to each other at pKa2, and then after that, I get more H2PO4, more HPO4 than H2PO4, and then at equivalence, I have no more H2PO4 left, at least not much, and all of it gets converted to HPO4 minus. Then the third piece of the graph starts to tick in, and my HPO4 starts to be at higher pH as I add OH minus, starts to become PO4 3 minus. Of course, there's an area at pKa3 where both of these species are equal to each other. And then at the end, my H2PO4 pretty much hits to its rock bottom, and the PO4 3 minus is at its maximum value, okay? And it's never reaches 100 really. Now let's look at the predominance species diagram. Okay, so this is the curves of predominance. This is the titration curve. Okay, so this is a distribution diagram for the different species. And now we're going to talk about the predominance diagram. I talked about it before, but this is really where I want you to concentrate with me in this area. What you do is right away put a straight line and say pH. So here's where my straight line pH increases. And just haphazardly put pKa1, pKa2, pKa3, since I have 3 pKa values. And then at the lowest pH, I put my most acidic species, which is H3PO4. And then in this area, my predominant species will be H2PO4, which is after the pKa1. After pKa2, my predominant species will be HPO4 2 minus, and after pKa3, my predominant species will be PO4 3 minus. Very simple. In my opinion, just divide it up like that without the details, okay? Do not go for the details at the beginning. You don't need all the details at the beginning, okay? Very easy. That's all you need at the beginning. Now, if you're, depending on the question that you're asked, you may have to need more information, but that's all you need. This can tell me which species I have predominating in my solution. So if I tell you at pH, let's say 6, what area are you in? Oh, I'm right here. Okay, who's my predominant species? Okay, it's H2PO4 minus. If I tell you pH 1, oh, I'm here. Okay, it's H3PO4. If I tell you what predominates at pH equals 13, I'm here. That's it. That's the species, PO4 3 minus. Okay, so that's all you need if you don't want to do a numerical calculation for how much of each species is at that particular pH. Okay, now if I want to do more details, then it's better to go into, a more detailed graph. Of course, still we put the pKa values, and of course at the pKa, you know that the concentration of the two species, H3A and H2A, is equal. Here, H2A and HA is equal. HA and A3 minus are equal, okay? That you know, again from the titration. Also, you could add one more value point, which is when I only have in my solution H2PO4 minus, and when I only have, oops, there's a mistake. And what is this? This is an amphilytic species, right? And this number is half pKa1 plus pKa2 for this species. Okay, so this is at the first equivalence point, and here I have it at the second equivalence point, where I also get an amphoteric species where it's very easy for me to get the pH, which is half pKa2 plus pKa3. Notice how it's easy to know which pKa values once you're doing it like this. Okay, so that's going to be 9.65. So these are numbers or pHs which you can get right away without much calculation taking place. And you could also immediately say, okay, so if I'm here, now, this is the area where I only have H2PO4, okay? Beyond this, in this area, this is the point where I only have I have HPO4, this is I have H2PO4. So in between these two, I have both of these species. Okay. And when we do examples, it just becomes easier. So, you know, that's all you really need in detail. Of course, this is again that same type of thing. I put my three species, H3A, H2A, HA, and A3 minus, and these are separated at the pKa1, pKa2, pKa3. And this is just the equation where I only have H2A minus in solution. And of course, when I do the problem solving, I'll get into more detailed graph on each of the species. One important point as well, when we want to do complete neutralization of a reaction, I do want you to pay attention that sometimes they ask you, for example, how much OH to completely neutralize a certain acid. And if you have a triacid or a diacid, you really have to consider the stoichiometric ratio. So the number of moles required to, the number of moles reacted for the H2A, for example, H3A, for example, divided by 1, that's a stoichiometric ratio 1. Coming from this equation, I need 3 total moles of OH minus to completely neutralize all of the acidic protons for the H3A. And this is the equation can be translated into this stoichiometric ratio in terms of moles. So the number of moles of of sodium hydroxide reacted in this reaction should be divided by 3 to get the correct stoichiometry taking place. So if I want to compare how many number of moles for 1 mole of Na of this acid, I have to actually multiply that by 3. Okay, so I need 3 moles of OH minus to react for every 1 mole of the acid. And if you have the same volume, of course, the number of moles becomes concentration terms. Okay, this is a titration of a tri-base, and in the tri-base, we start with the A3 minus or PO43 minus here to be exact, and we usually have an initiation here. They don't really show an initiation point, but you actually do have kind of a curvature coming down, and then, you know, you have the first equivalence, and then we go at another sharp change in pH, a little bit of a sharp change, a second equivalence, and then whoop, whoop, no third equivalence, but there is actually a third equivalence here. Again, it's better to show it a little bit. This is not the best graph, really. But that's what you have in your textbook, and that's what's online available. Okay, so maybe experimentally, that's what they actually see. Okay. So that's it for the course.